Okay, so as a recap of what we've been doing, there's been, in the last two things you saw, there was in person, we talked about the L1 space, the LP space, and the L infinity space. And we kind of alternate between superscripts and subscripts for these. But the idea is, in the L infinity space, this is the maximum of the absolute values of the thing, so like of your function. And the L1 is kind of the sum. Let's be very specific and say for sequences. That was one specific space we did. And for sequences, people use L, with a lowercase. So the L1, LP, and L infinity. And so these were specific examples of different norms. The norm infinity of some sequence A was the maximum of the absolute value of AI from our sequence. And the L1 norm is the infinite sum of the absolute value of the AI. Okay. Okay, and I'm using this notation of A open bracket I, so that when I do sequences of sequences, I have the subscript ready to use for my sequence, and then I use brackets for the elements. And that way it matches functions. We're going to soon do functions. I also talked about this for functions. For functions, I talked about L infinity, and I talked about pointwise convergence, which was the other one. Pointwise convergence, that was the other thing we saw. These are like concrete examples. And if you check your notes, you'll notice I left a hole where LP is. I didn't say what L1 is for functions, and it turns out that L1 actually has a problem, and by the end of today's class, we're going to be able to say what the problem is. So I left out L1 and LP sort of on purpose, and we're going to get to the issue with capital L1 and LP, which would be something like summing up the entries. There's some stuff to do there. The other parallel line that you did at home is open and closed and compact sets. Open, closed, and compact. And compact. Okay, and in particular, compact is important, so let's do a little reminder. K is compact. Means every subsequence in K, every subsequence, let's give it a name, xn, and going from 1 to infinity, which is in K, has, it's not that the subsequence must converge every subsequence. I want every sequence. I'm getting ahead of myself. Okay, let's, you can't talk about a subsequence until you have a sequence on the board. Okay, every sequence, so you have a sequence. A good example to keep in mind is like a compact set is like the closed interval 0, 1 in R. That's like a good example of a closed thing. So you could have a sequence in there that doesn't converge. It could go 0.1, 0.9, 0.1, 0.9, and just alternate back and forth all day. It could be like all spread out between 0 and 1. It could bounce around. Like actually the sequence sine of n squared. That's a fun sequence. Let's take its absolute value. So it's always between 0 and 1. This will dance around and kind of like spread itself out between 0 and 1 and sort of everywhere. So it's not that a sequence must converge, but it has a convergent subsequence. Convergent subsequence. And the limit as k goes to infinity of this subsequence of x and k that exists and is also equals to some x, and that x is also in k. So not only is there a convergent subsequence, but that convergent subsequence has to end up, the limit is still in k. So if you take the limit of this thing, you cannot escape the interval 0, 1. You can't end up somewhere else. This is in contrast to something like open bracket 0, 1. Like if I had open bracket 0, 1, you could have a limit that got to exactly 1 that would sort of escape that set. So that's not a compact set. So that was the hard part. And some people got bamboozled by this on the quiz, so this is worth restating. So these are the two things from last time, and today they're going to combine together. So we're going to combine together. These were sort of done by the snow day out of order. So you were supposed to watch this video first, and then we were supposed to do this lecture. No, we were supposed to do this lecture on the Thursday of the snow day, and then you were going to watch this video after. But because of the snow day, you did it in reverse. But they're sort of like go in parallel, so it's okay. I think I maybe during the video said like 1 or 2 things that were like mysterious, but should have been okay. So that's like a recap. That's where we are, and we're gonna combine these two things and see like where we get to from this kind of stuff. Questions or comments about anything? Okay. So the way these things are going to combine, let me open my notes, is I want to talk very briefly about something we talked about last time, which is theorem 1.3.13, which says that on a finite dimensional space, all norms are equivalent. All norms are equivalent. And we proved last time that all norms being equivalent means if you have two norms, then you take the norm 1 and you take the other norm, and they're bounded above by some alpha and some beta. Okay? And how does the proof go? I'm not going to do the full proof sketch. But the key idea in the proof is that you find this alpha and beta, you find it by using the extreme value theorem. So you look at the function f of x, which is the norm of x, and this will be a continuous function. A continuous function. And so it's a continuous function from a finite dimensional space. This is some function f going from Rd to R, if it's like a finite dimensional space. Or it's, maybe it's not exactly Rd, but it's a lot like Rd. Let me give this, actually, instead of calling it f, which is kind of a generic name, let's give it a more fun name. Let's give it the name capital F. Okay, that's better. Okay, capital F. So this is a continuous function, and the extreme value theorem says that continuous functions, they achieve their maximum and minimum on a closed and bounded set. Continuous functions, and I'm going to highlight achieve. So not only do they have a maximum and a minimum, there's some upper bound and there's some lower bound, like you can't go off to infinity, but actually there is a point that is equal to the maximum and there's a point that is equal to the minimum. They achieve their min and max. Their min and max. And if you were a studious Math 1200 student, you'll remember it's not enough that the function is continuous, but the set you're on also has to have no like open intervals, because then it could go off to sort of infinity at one end. So on where? On closed and bounded sets. Okay, and a great example is the thing that we just did, right? On the interval 0, 1, if you have a continuous function on closed 0, 1, you must have some point where it's its maximum and some point where it's its minimum. On open 0, 1, it's not true, because the function can sort of escape off on either end. Okay. And the extreme value theorem, if you apply it to this norm, the maximum is the beta. The maximum, and you have to do it on the right set, but I will, okay, it's going to be the set where the norm is exactly 1 of f of x. This will be beta, and the minimum, where the norm of x equals 1, f of x will be alpha. So alpha and beta come from the extreme value theorem. Okay, so that is kind of like the proof sketch of why everything is equivalent. Everything is equivalent because of the extreme value theorem, and you get the sort of the upper bound and the lower bound by doing the minimum and maximum of the right thing. So if you read the proof in the textbook, you'll see this exactly. And this works on RD. So this is the extreme value theorem on RD. Okay, so it works for finite dimensional vector spaces. Now, of course, in this course, when you see closed and bounded, things that are working closed and bounded on RD, in general, do not work. So the extreme value theorem on infinite dimensional spaces is false, written like this. So the extreme value theorem is false, say as written on infinite dimensional spaces. And I will give you an example on our favorite little lowercase l space. So on the sequence space L infinity, we're going to make a function, and the function is I'm going to tell you what the function does on my favorite sequence of vectors, the e's. Remember, the en is the sequence, which is all zeros, and then it has a 1 in the nth component. So these are the e's, the nth component is en. I'm going to make a function so that capital F of en, I'm going to make that 1 over n squared. So this is a function from L infinity to R. Okay. So when it inputs en, it outputs 1 over n squared. And then if you have some other sequence, if you have some sequence, A1, let me write them in the way I've been writing them. A1, A2, ... So you input the sequence, what you're going to get is the infinite sum of ai divided by I squared. I equals 1 to n. So it's a linear function. It combines the action of these things on that. So this is my function. And this function, it's a continuous function. You have to check that it's continuous, but I won't prove it. So check it's continuous. Okay, and continuous, again, means if you have a change, for any change epsilon that you want to control in the output, there is a change delta so that things will work over here. It's actually, we'll just follow by triangle inequality, so it's not too hard. And we're not going to worry too much about these continuous type things for now. So just take my word on it that it's continuous. What is its minimum value? Let's look at that. What is the minimum? What is the minimum? Let's say on the closed ball of unit 1. So the minimum, and we're going to look at all the sequences in the ball centered at 0 of radius 1, and we're going to do the closed ball. So these are all the things with the norm of A less than or equal to 1 of f of A. What is this minimum? Okay. And if the extreme value theorem was true, the minimum would be some number, and there would be some sequence A that achieves the minimum. But in this case, the minimum is 0, and you can't really write the minimum. The minimum is just a lie. There is no minimum. You can write the infimum, the inf. The inf equals 0, and it is never achieved. And it is never achieved. Okay, wait. I don't want. Okay, this is a lie because here I said the closed ball, so I included everything that is on the edge, which includes the 0 vector. If you feed in the 0 vector, you get 0. I don't want to include all the things less than or equal to 1. I want to include the things that are norm equal to 1. So I think the textbook calls this the sphere. So let's do that. The sphere S. So this is the set of A such that the norm of A equals 1. And let's say the infinity norm, just to be totally precise. Because I said this is a function on L infinity. Okay, great. So this is S01 is the set of things whose norm is exactly equal to 1. And the infimum, I claim, is 0. There is no minimum. It is never achieved. And actually, you can see that already on the set of the ENs, right? So the ENs, every single EN is in the set I'm looking at. They're all norm 1. All the ENs are exactly norm 1, and they have size 1 over n squared. So you can make the value of f of a as small as you want by just taking a really big n. You're like, I want to make it 1 over a million. I'm like, okay, take n equals 1,000, and then the answer is 1 over a million. You're like, I want to make it 1 over a trillion. Like, okay, take n equals whatever it's supposed to be, 10,000, and then it's going to be 1 over a trillion, and so on. So by looking at the sequence of f of ENs, it's getting closer and closer to 0. It never gets to 0. It's never equal to 0. So f of En, the limit as n goes to infinity of f of En equals 0, and f of a is always greater than 0 for a norm of a equals 1. So it's never achieved, even though this limit equals 0. So this is an example of the extreme value theorem being violated. Okay, what is the whole point of saying all this? Is that we have to fix something. To make an extreme value theorem that works in general, you have to fix it. And the thing you have to fix is this closed and bounded is no longer the right thing. The right thing is compactness. So the new version of the extreme value theorem, the new version of the extreme value theorem, it would say that continuous functions achieve their min and max. They achieve the min and max on compact sets. That's the right thing to do on compact sets. Okay, and in RD, this was part of the very end of the video that you watched. In RD, compact is the same as closed and bounded. Every closed and bounded set is compact, and every compact set is closed and bounded. And that is true in finite dimensional spaces. But it is only, in general, it is only true in one direction. In general. So in general, it's not true both ways. But what is true is that compact implies closed and bounded. And those are examples of good types of proofs that would be sort of at the level of the midterm. Please prove that compact implies closed. Please prove that compact implies bounded, this kind of thing. Okay, that was at the end of the video. This is a good place to, we're gonna start doing some new stuff in a second. So a good place to stop for questions or comments with this so far. Okay, so the question you should maybe be asking yourself is, okay, in general, what is compact then? If it's not closed and bounded, what is it? What is it? And the in general thing is compact is if and only if it has to have two properties again, but the two properties are not closed and bounded. You're going to think I'm making this up when I tell you one of these is called it's not bounded. get bounded right out of your head. It's totally bounded. Totally bounded. Whenever someone is talking about totally bounded, I always think of like Arnold Schwarzenegger. Like, this set is totally bounded. Like, it's like I don't know why they took this word and then they added totally to it. This is like, but it's something different. Like, I don't know how they came up with this. So totally bounded obviously is like bounded but better. And then closed is nice. Closed says like the limits can't escape, but we need something better than closed. We need something called complete. And complete is sort of even a better version of closed. Closed says if you have a limit, the limit is not escaping. But complete says you must have a limit in a certain sense. So you can't avoid having the limit. So closed is like you can't escape with a limit, and complete is like not only can you not escape, but you're gonna have a limit for sure. Okay, so we're gonna see what these two things are in a second. Has anyone heard of totally bounded before? Okay, nobody. Who's heard of complete? Okay, complete you've heard of a little bit. So complete is the big one, and that's going to lead us into our next topic. I'm going to do totally bounded sort of quickly over here. And this one, totally bounded, is not even in the textbook. So definition, this is not in the textbook. Totally bounded. Totally bounded. A set is totally bounded. So bounded means there's one big ball that covers everything in the set. Like everything, there's some radius r, and everything is at most radius r. But totally bounded means not only can everything be covered in one big ball, but you can cover it in lots of tiny balls, and the balls can be as small as you want. So totally bounded means for all epsilon greater than 0, you can cover it with balls of radius epsilon. So a set, let's call it S for set, is totally bounded if it can be covered by balls of radius epsilon, by balls of radius epsilon. Okay, and so far what I've written, every set can be covered by balls of radius epsilon because you just like take all the points in the set, put a ball of radius epsilon around that point, and then that will cover it, right? So far we haven't said anything. The key thing is the next step, which is using finitely many balls. Finitely many balls. So you can cover it with balls of radius epsilon, and you only need like 100 balls or something. You don't need infinitely many balls. So for all epsilon greater than 0, there exists, let's call it x1 ... xn. So let's say n is finite. N is some natural number, some honest number. And you have n points such that S is a subset of the union, going from 1 to capital N, this finite union of the balls centered at radius, at x of radius epsilon. Okay, so totally bounded. And to draw a little picture of what this looks like, here's a picture. So bounded is like there's one, if I have, let me draw a blob first. That was supposed to be a ball, not a blob. Okay, so here's my blob. Here's some set S. And so bounded means, look, there's some amount, you can draw some circle that covers the whole thing, right? Ball of radius 0, R. And totally bounded means you can cover it with finitely many little epsilon balls, right? And I can cover it like this, and I'm not going to have to go forever. There's some amount of little tiny balls. No matter how tiny you tell me, I can eventually cover them up. Okay, and you might realize that in R2 or RD, bounded and totally bounded are exactly the same because the big ball, the ball of radius 0 centered at, of radius r centered at 0, can itself be covered by these finitely many balls. In fact, the number you need is roughly r to the power d. So the number in RD, the number of balls needed is approximately, it's like 1 over epsilon to the power d. So the dimension tells you like how many you need. The smaller you make epsilon, the more balls you'll need. If you make epsilon half as small, you'll need 2 to the d times more balls. But it's kind of the same concept. Okay, and this idea is like key to a lot of proofs. Here's another example. And again, it's my favorite sequence in L infinity. In L infinity, the set of the ENs, and going from 1 to infinity, so that's a collection of all these spike things that have exactly 1, 1, is not totally bounded. Is not totally bounded. And the reason it's not totally bounded is notice that the difference between En and Em, the distance between any two of these elements, these sequences, right? I drew these on the board the other day. So one of them is like a spike like that at N, and the other one is a spike like this at M, right? How far apart are these two sequences? Well, we're looking at the maximum difference. The maximum difference is 1 unless they're the same. So this is always 1. And so when they're always 1 apart, if you cover it with a ball, as long as the ball is, if somebody chooses an epsilon less than 1, every ball can cover at most one of these things. It's impossible that a ball would cover both En and Em if its radius is less than 1. So if I take epsilon equals 1/2 or something, you're going to need infinitely many balls to cover the infinitely many elements of En, because every ball can only cover 1 at a time because they're sort of distance 1 apart. So therefore, balls of radius, let's say radius 1/2, can cover at most 1 En each, and therefore we need infinitely many balls of radius 1/2 to cover all the ENs. Okay, so this is a common way things are not compact, is when you have many things that are far apart, and then it's not totally bounded. Okay, I think that's all I want to say about totally bounded. Let me see if I'm missing anything. Because the main topic we want to get to is complete, and complete will be a big deal that will span several classes and topics and things. But totally bounded, I think we just sort of mentioned in passing. Questions about totally bounded? Yeah.
So the balls don't necessarily have to be purely contained in S, right?
Yeah, that's okay. It's okay if they kind of, we just need them to cover S. Okay. Yes. Yes, that's right. Yeah.
Does it say balls of radius 1/2 can cover at most 1 En each?
Yes, that's right. Yeah, I forgot the word 1, huh? At most 1 En each. Yeah. Yeah, let me fix that. Thank you. Can cover at most 1 En each. Right. Yeah, that's right. So it's impossible for a ball to contain 2 of them because they're distance 1 apart and the ball is only radius 1/2. Yeah.
Does it matter if the balls are open or closed?
Oh, yeah, that's a good question. I think it doesn't matter. Yeah, because if you can cover it with open balls, you can cover it with closed balls by making it a little bit bigger, and vice versa. So yeah, it's you can make the definition either way, and it's going to be the same. If you can cover it with open balls, then you can cover it with closed balls. If you can cover it with closed balls, then you can cover it with open balls. And very often, the thing that you do is basically this covering with infinitely many balls, or finitely many balls. It's a trick to go from infinitely many things to finitely many things. So you have like all the points in S, of which there's infinitely many, and you sort of want to reduce down to just looking at finitely many cases, which you look at the balls that you were given. So sometimes you'll use an open one, sometimes you'll use a closed one. Yeah, great question. Is there a question over here as well? No, okay. Okay, that was totally bounded. Now we're gonna move on to complete. Complete. Okay, and complete is a great name. And the word complete kind of matches a very high level idea of what we want it to be. And so the idea is, this is approximately equal to in ideas, which is no holes, right? A complete space is a space where we got all the stuff. There's no hole of something that is missing. I'll give you an example of a not complete space in this ideas realm. A not complete space. And that is the rational numbers. So the rational numbers, again, you think of them as a number line, and then you think of them as like some kind of dust thrown on here, right? So you got like all the rational numbers. And if you look at all the rational numbers whose denominator is 1/2, then they're kind of like 1/2 apart. I guess I want their denominator to be 2, not 1/2. And then you look at all the ones whose denominator is 3, they're like 1/3 apart, and then 1/4 apart. And then sort of they like, all together, they're sort of like covering almost everywhere. But Q is not complete because it has holes. Who can give me an example of a hole in the rational numbers? Yeah. Yeah, E. Yeah, E is great. So E or pi or square root of 2, these are all numbers that we know are irrational. So like, this was what the Greeks were working on, and they were like, mind was blown that square root of 2 was irrational. And so the point is that, when we look at Q, in some sense, it's got holes in it, and the holes are the other irrational numbers. Okay. We're going to see later in the course that actually, in some sense, Q is mostly holes. Like if you pick a random number, the chance that it's a rational number is 0%. So that'll be exciting. But what do we actually mean? Like, how do we make this precise? So we need some notion of when should it be converging? And then we'll say that it has no holes if every sequence that should be converging actually converges. Okay, and then Q will be not complete, because we'll have sequences that get really, really close to the square root of 2, but are never actually there. And then that sequence like won't have a limit in Q, and that's like our idea of Q. So no holes, and then more specifically, no holes means every sequence that should converge, should doing a ton of heavy lifting in the sentence, converge, does actually converge. Okay, so we need a way to measure. We have some sequence. We can't talk about the limit, right? Because if we could talk about the limit, then we could just say like, oh, the limit has to be there. So we need a way to, just looking at the sequence, have this idea of whether or not it should converge or not. Yeah?
Can you not like describe this with density?
With density. Oh yes, okay, so but with density, you need to have the notion of Q is dense in something else. So you need to like already know about the bigger space, right? So like if you were like the Greeks and you didn't know about real numbers, and you only knew about rational numbers, you couldn't make a statement like, oh, the rationals are dense in the reals, because you don't know the reals. So we kind of want to be able to look just at the rationals on their own and study them and say, hey, are we missing a hole or not, right? And of course the rationals is a good example because you know it from like childhood, and you know the answer. But we're going to look at these complicated spaces where it's like, oh, like is there something missing or not? And we need a way to tell. Yeah, that's a great point. Yeah, so Q is a little bit of an artificial example because you already know the answer. But you have to imagine a situation where we don't already know the answer. Okay, great point. Okay, so back to should converge. And fortunately, there is a French mathematician by the name of Cauchy who figured this out. So he made this definition of something called a Cauchy sequence. And this is the thing that is a sequence that should converge. These are the should converges from way up here. Let me see, I can get the highlighter. The should converge. Those are the Cauchy sequences. Those are the sequences that should converge if things are good. And what is the actual definition? The actual definition is it's a sequence that gets close to itself. Gets close to itself. I'll tell you the real definition in 1 second. But a converging sequence is there's some item that everything in the sequence is getting close to, right? Xn converges to X if the xn's get really, really close to X. But a Cauchy sequence is just about the xn's, and it's saying the xn's, they get close to each other. They all, they're all bunching up near each other, and that is a Cauchy sequence. Here's the actual definition. It's for all epsilon greater than 0, there exists n such that, and if this was an ordinary sequence, it would be all the n's past capital N. But because we're measuring the difference from the sequence to itself, there's an n and an m. So for all nm greater than n, so both of them have to be bigger than m, we have the norm of xn minus xm is less than epsilon. So the distance from the sequence to itself at 2 different points beyond a certain point is less than epsilon. The sequence is getting arbitrarily close, but not to some specific final endpoint, but to itself. That's a Cauchy sequence. Okay, n should be a natural number. And let me tell you also where this is in the textbook if you want a better, more complete definition than mine. 1.4.1. Okay. Okay. That's a Cauchy sequence. Who's seen Cauchy sequences before? You might have done them in your previous course. Okay, fantastic. So you maybe already know a little bit about Cauchy sequences. Here is a little lemma. Again, this is a good kind of easy proof for the midterm. Every convergent sequence is Cauchy. So if you converge, if you're getting really close to some x value, then you must be also getting close to yourself. Okay. Okay, here's a sort of short proof. Suppose the limit as n goes to infinity of the xn's equals x. Then, given any epsilon greater than 0, right? So we're going to eventually prove the definition of Cauchy. We're going to be given some epsilon greater than 0. Let n be so large so that the norm of xn minus x is less than epsilon whenever n is bigger than n. So I found the capital N using this limit. And now I claim this thing will work. Actually, I think I think this is going to be one of those epsilon by 2 arguments. Let's leave it as epsilon, and I'll come back and I'll fix it if I need to. But okay, xn minus x is big less than epsilon, and then now consider for nm bigger than n, we have, and now we have the thing that we want to prove. We want xm minus xm. We want this to be less than epsilon, so I'm going to do a chain of inequalities that starts with what I want on the left and ends with what I want on the right. And the secret is to add and subtract x. Okay? And now, by triangle inequality, this is xn minus x plus x minus xm. And I can say by triangle inequality. Very nice. And now, because n and m are both bigger than n, each of these things is less than epsilon. Okay, and so I could say, I could give this a name. I could call this star. Call this star. And I could say by star. By star. Since n, m bigger than n, each of these things is less than epsilon. Okay, and then this is 2 epsilon. Okay, and now I could write a thing that's like, oh, 2 epsilon is like arbitrary, blah, blah. But it's easier, I think, to go back and just fix your proof. Just make this an epsilon by 2, and then you make this an epsilon by 2, and then this 2 epsilon is actually 2 epsilon by 2, which equals epsilon. And then it's exactly as you want, and you can say as desired. And then you're done. Okay, nice little proof. Okay. So this is every convergent sequence is Cauchy. Questions or comments about the proof? The interesting thing is the reverse. So question is every Cauchy sequence convergent? So this way it was easy. If it converges, then it's Cauchy. If it's Cauchy, is it convergent? Yes or no? And this is the interesting thing. I guess, so you guys saw Cauchy sequences at some point in the past. What was the setting in which you saw a Cauchy sequence? Maybe, yeah.
I saw one where it was a sequence in the rationals where
Okay.
the sequence is just like the nth term in the sequence is approximating pi by one more digit.
Right. Yeah. So the answer to this question, I think you've seen, is the answer is it depends. It depends. And so, for example, in R, just purely real numbers, if you're talking only about real numbers, then the answer is yes. And so you might have seen this in like a first year analysis course, first or second year about sequences converging, and they'd say every Cauchy sequence is convergent, and that's true in R. But as mentioned a second ago, in Q, in the rationals, the answer is no. And that's because in Q, you might have a sequence of rational numbers, and it's a Cauchy sequence. You never have to talk about the real numbers to talk about Cauchy, right? You just need to make sure that the distance between your rational numbers is getting smaller and smaller. If your rational numbers are approximating pi to n decimals, then xn minus xm will be less than 10 to the minus n. They'll sort of like, they'll agree for the first n decimal places. And so it will be getting closer and closer to 0. It will be Cauchy, but it won't converge because the thing it converges is not a rational number. It's sort of escaping the space. Yeah, question over here. This is the definition of completeness. Very good. So let's write this down. Definition, complete, and I believe in the textbook they put this in the same definition as the definition of a Cauchy sequence. They put in, oh no, I lied. Okay, it's a different definition, 1.4.5. Okay, a normed vector space is called complete when every Cauchy sequence converges. So complete literally is just saying, if you have these Cauchy sequences, these are sequences that get close to themselves. Those are the ones that should converge. If all of the ones that should converge do converge, then we say it's a complete space. This type of thing, it has a special name, a complete normed vector space. A complete normed vector space. This is called a Banach space. Okay, now I will give you a little history lesson. This is the one thing I have open for today, is the Wikipedia page for Mr. Banach, so we can pronounce it the right way. Okay, so this guy is Stefan Banach. Okay, let me turn my volume up and see if you guys can hear it.
Stefan Banach.
Okay, so that's the right way to say it. I guess in my circles we say a Banach space. I will warn you, if you say Banach space, then people will know you're a faker. So make sure you at least say Banach, and then if you're fancy, you can say
Stefan Banach.
Okay, there you go. So this guy, he was around in the early 1900s, and his PhD thesis in the 1920s had this thing about complete normed vector spaces in the 1920s. And then he wrote a book where he called them spaces of type B. So there's this book by Mr. Banach, and you have spaces of type B, and then eventually people said, oh, that's a Banach space. And he's got all sorts of fun theorems. This is a famous guy. The Banach-Tarski paradox says that you can take a sphere and cut it up into finitely many pieces and reassemble it to get two spheres, which is a fun one. So yeah, lots of famous stuff from this guy. There we go. Okay, what else to say about Banach? I guess nothing. Okay, so where are we? Complete and a complete norm vector space is the Banach space, which is a fancy name. The rest of the lecture is just going to be some examples of different things and whether or not they are complete. Yeah, in particular, there's one proof that is a good proof to know. But it's a great place to stop for sort of big picture questions before we get deep into some example. Okay, let's do some examples. So here is, you've seen some already. You've seen Q and R. R is complete, Q is not complete. Here is one. What about the space of polynomials? The space okay. So I'm going to do P on 0, 1, the set of polynomials P of x, where P of x is a polynomial, P of x equals, and its sum, I equals 1 to n of x to the power I times some coefficient ai. Okay, these are polynomials. So is it complete or not complete? I have to put a norm on it. It has to be a norm space. We're going to do the usual maximum norm with the sup norm, the L infinity norm. So the norm of P equals the maximum of x in 0, 1, or actually the maximum equals the sup. Let's write the sup of the absolute value, just 1 bar of P of x. Okay, let me make this really 1 bar for clarity. Okay, so is this complete or not? Let's think for a second and we'll have a little hand vote. Complete? Not complete? Okay, I'll let you think for 30 seconds and then I'll take a little hand vote. Okay, who thinks the space is complete? Put up your hand. Who thinks the space is not complete? Okay, almost everybody is right. It is not complete. That is correct. This is correct. Correct. Can anyone say why it's not complete? Yeah.
We have this wonderful theorem by Taylor that tells us they can approximate any function using a sum of polynomials.
Oh, yes. Okay. Yes, I think this theorem, it is a famous theorem, but I don't think it's by Taylor. I think this is the Stone-Weierstrass theorem. Yes. Okay.
Either way, if you can take a bunch of polynomials and approximate functions that aren't polynomials.
Yes. So this is a good hint that something is up. So the Stone-Weierstrass theorem, Weierstrass, again, two other famous mathematicians. Stone-Weierstrass theorem, it says any continuous function can be uniformly approximated by polynomials. Continuous function can be uniformly approximated by polynomials. This is say on 0, 1, which is the space we're on. So uniformly is exactly this norm. The infinity norm is exactly the uniform norm. And so the reason it's not complete is you take some function that's not a polynomial, that is a continuous function, and then you would approximate it uniformly by polynomials, and that sequence of polynomials, it's converging in the uniform norm to the thing you want by the Stone-Weierstrass theorem, and therefore it is a Cauchy sequence by the lemma we proved before, right? Every convergent sequence is Cauchy, so it's converging to your non-polynomial, therefore it's Cauchy in L infinity, and is converging in L infinity, and therefore it's Cauchy in L infinity, but it is not a polynomial as a limit. So it's a Cauchy sequence that doesn't have a polynomial as a limit, and therefore the space is not complete. Let me sketch that out. Okay, so take any non-polynomial. Take any non-polynomial continuous function. Let's call it c of x for continuous, and then you have the limit as n goes to infinity of Pn equals c in L infinity. Therefore, the Pn's are Cauchy in L infinity, and therefore, we have a Cauchy sequence with no polynomial limit. Okay, and that is kind of the idea behind the not completeness. I think the textbook even gives a specific example of polynomials. Like they give you a specific c, and then they give you a specific sequence of Pn's. So you can check that out if you are interested. Actually, that is also related to the Thursday to Tuesday video you're going to watch after today. Also has this kind of thing in it with infinite sums of things. Okay, fantastic. Questions? Yeah. Yeah. Oh, 0, 1 is the interval 0, 1, and by on 0, 1, I just mean the domain of the polynomials is 0, 1. So, yeah, this is important. So the polynomials p of x, I didn't write it, which is, maybe my fault. So I should say p of x, and x is in 0, 1. So we're thinking about the functions on 0, 1, and that's why we do the norm. Yes, I think that's a very good question. Yeah. And yeah, it's important actually, in this case it matters a lot, because if you have on all of R, if you take the polynomial as a function on the whole real line, it is not true that you can approximate functions by polynomials. So in fact, every polynomial kind of diverges off to infinity, so you can only approximate functions that diverge off to infinity. You have some function that flattens out, you won't be able to approximate it by polynomials uniformly. So it's very important in this theorem that it's 0, 1 and not some other interval. Okay, very good. Okay, the next example is the space of continuous functions. Okay, so the space of continuous functions is CAB, is functions that are merely continuous, f from AB to R. Yeah, I'm doing AB, so it matches the textbook. You could pick AB to be 0, 1, and that would be perfectly fine. FAB from to R, such that f is continuous. So it has the, for every epsilon exists a delta property. Okay, and we're doing the same norm as before, so this the sup norm. The norm of some function f. Okay. The maximum, or the sup, okay, and then you have if you have a Cauchy sequence here, will the limit be continuous? And this one is a lot harder because can you have all sorts of there's all sorts of weird continuous functions. I will give you one example of something weird happening. Example of a weird sequence. Okay, and it's the sequence fn of x equals x to the power n. Okay, and if you look at the sequence x to the power n on 0, 1, so let's pick 0, 1 as our interval. What do they look like? So you have a line, and then you have a quadratic equation, and then you have a cubic equation. So this is x squared, this is x cubed, and so on. And these functions all have fn of 1 equals 1. So they always go through this point at 1. But all the other points, when x is strictly less than 1, between 0 and 1, not including 1, all of them kind of get closer and closer to 0. So fn of 1 equals 1. And for x less than 1, the limit as n goes to infinity of fn of x equals 0. So it's kind of getting in closer and closer to this function in some sense, this kind of thing is going like this and is becoming this function, which is 1 over here. Let me draw it in pink. 1 over here, and then 0 like that. So this is the function f, which is 1 if x equals 1, and 0 if x is less than 1. And this function is not continuous. So there's some sense in which these sequence of functions, each of which is continuous, it's getting closer and closer in some way to this kind of funny discontinuous function. And then you got to ask yourself, is this a Cauchy sequence? Like, could we make a Cauchy sequence like this? Is this one even Cauchy? What's going on? So these kinds of weird examples really cast doubt onto, is this thing going to be complete or not? Complete or not complete? Okay, I'll let you, now you've seen the tricky example, I'll let you think for 30 seconds, and then we'll do another vote and see if we think it's complete or we think it's not complete. Yeah, yeah.
On the definition of the stack, it has AB, but then the soup has 0, 1.
Ah, yes, okay, that should be AB. Yes, okay, very good. Yeah, thank you. Yeah. So in the textbook they wrote AB. I always think of it on 0, 1. If you can do it for 0, 1, it's going to be the same for any AB. Yeah. Okay. Let's vote. Who thinks it's complete? Who thinks it's not complete? Who is kind of unsure? Okay, so it looks like I'd say almost no one voted for this one. Almost no one. Almost no one. I'll say some voted for this one, and some people are unsure, which is good. Unsure is a good state in analysis because sometimes the hardest part is figuring out if it's true or false. In this situation, the correct answer, it is complete. This is correct. So it is complete. What's going on in the example I just gave you? These functions, they are converging to 0 pointwise, but they are not converging in norm. So even though these things look like they're getting close to 0, they're not a Cauchy sequence in the norm that was given. And in fact, if you look at their norm is always 1. The maximum value of these functions is always 1. They're not getting close to this function in norm. So yeah, this is the kind of thing that you have to be very careful about. And I'm going to prove for you, I think in the last little bit here, that it actually is complete. Okay, so theorem, this is from the textbook. I unfortunately forgot the number. Let me see if I can quickly find the number or not. Okay. Okay. Yeah, okay, example 1.4.7 in the textbook, and it's C of AB with the sup norm, with the infinity norm, is complete. Okay, and so what you have to do is you have to prove that if you have a Cauchy sequence of functions that are Cauchy in this infinity norm, then there is a limit, and that limit is a continuous function. Okay, so this is how the theorem will start, or the proof will start. Okay, let Fn be a Cauchy sequence in the infinity norm. We must find a limit and prove it's continuous. Must find a limit and prove it's continuous. That's what we got to do. Okay, so this is the proof. And the first step is notice that for every single x, notice that for each x value, for each x in AB, the sequence, which is Fn of x, going from n equal 1 to infinity. So we have a sequence of functions that are Cauchy in this norm space. This is a sequence of real numbers. And that is a Cauchy sequence in R, is Cauchy in R. And the reason is if you look at the difference between Fn of x minus Fm of x, that is always less than the difference in norms between Fn and Fm. or less than or equal to. So this is a key property of the maximum norm, is any individual point is bounded above by the norm of the functions. And so when you have the Cauchy stuff on the norm of the functions, it's going to work for every individual value. So I won't write it out in full detail, but I think it's okay. So the Cauchy property for Fn in the infinity norm transfers to Fn, the sequence of numbers, n equals 1 to infinity. Let me put this one as a sequence. Okay. Is that okay? So as soon as this thing is less than epsilon, then this thing will be less than epsilon too. And so the Cauchy property will transfer over. Okay. Now, so for every individual x, this thing is Cauchy. R is a complete space. So since R is complete, there is a limit as n goes to infinity of Fn of x equals f of x for each x. So in other words, for every individual x value, we have this Cauchy sequence of values Fn of x. And those have to converge because they're in R and R is complete. And so we have a pointwise limit. So in other words, the Cauchy property transfers to every individual point. And so every individual point must be converging to something. And so we have pointwise convergence, i.e., there is a pointwise limit, a function f, so that Fn goes to f pointwise. Okay, so we found this function f, and then our job is going to be to prove that not only is it converging pointwise, but actually the convergence is in L1, or sorry, and L infinity in the infinity norm, and also that f is continuous. Those are the two things that we need to prove. Okay, let me, as a little reminder, it remains to prove Fn to f in L infinity norm, and that f is continuous. Okay. In the textbook, they first prove that f is continuous. Let's do that. So claim, I think this is the nice way to organize these kinds of things in your proof. Claim f is continuous, and then we're going to put the proof here. Okay, proof. Let x in AB and epsilon greater than 0 be given. So we're going to find the delta that works for the function f at the point x with the given epsilon. And the trick is we're going to use the Cauchiness and the continuity of the functions in the sequence Fn. Okay. Okay, since Fn of x, let me write it as a limit. Since the limit, oh boy. Struggling with my markers. Okay. This one. Since the limit as n goes to infinity of Fn of x equals f of x, find n so large so that the absolute value of Fn of x minus f of x is less than epsilon by 3 for n bigger than n. So this is sort of coming from the textbook. This is going to be an epsilon by 3 argument where there's going to be sort of 3 little sources of error. We're going to approximate f by Fn. We're going to approximate Fn of x by Fn of x plus a little bit plus a delta. That's going to give us another epsilon by 3 amount of error. And then we're going to do one more approximation. There's going to be 3 approximations that come together with triangle inequality that work here. If you were sort of discovering this proof for the first time, you would write epsilon and then you would go back and fix it at the end. Okay. Okay. Okay, and now we say, since f capital N of x is continuous, so this is n greater than or equal to n. So this approximation works for all the n's in the sequence. In particular, it works at f capital N, which is one particular continuous function, is continuous. Find delta so that So that what? F capital N of x minus F capital N of y is less than epsilon whenever x is less than y. X minus y less than delta implies this works. And actually, again, I want epsilon by 3. So in other words, we're using the continuity of capital F of n to find a delta that works for this guy. Okay? And now you have this guy, you have this approximation. We're going to put these together to make an approximation for the final thing. Okay, and I've realized I might have made a little boo-boo, which is I don't want... Let me just check here before I say something silly. Okay, so I'm gonna write something, and you're gonna see what the problem is, and then we're gonna go back and we're gonna fix it. So, because the thing I wrote down, it turns out, is not good enough. You're gonna see why. So there's gonna be some kind of issue over here, and then we're gonna go back and we're gonna fix it. Okay, so what I would like to say is I would like to say f of x minus f of y. So now consider when x minus y is less than delta, we have, and so this is the chain of inequalities I want. I want to start with the function f that I'm trying to prove is continuous, and I would like to do a bunch of inequalities, and I would like to get f of x minus f of y, and I would like to do a bunch of stuff and end with less than epsilon, right? That's what I would like. And the natural sort of way is I have this approximation, f is kind of like fn, and then I have this thing for the fn's, so maybe I can stack those all together. So this thing is equal to f of x minus fn of x plus fn of x minus fn of y plus fn of y minus f of y. Okay? So in other words, I've added and subtracted fn of x and fn of y, and that kind of splits it up into 3 parts. There's the difference between f and fn, there's the difference between fn of x and fn of y, and then there's the difference between fn and f, but for the y values. Okay, so by triangle inequality, this is less than or equal to f of x minus fn of x plus fn of x minus fn of y plus fn of y minus f of y. Okay, and then these two are great. F of x minus fn of x, that thing is less than epsilon by 3. So this is less than epsilon by 3. Fn of x minus fn of y, that's by the continuity of fn. That was also less than epsilon by 3. That was our trace of delta. But now is where I'm cooked. I am screwed because I made a mistake. And that is, I have no idea what is going on with fn of y, right? You see, I chose the n, so the x's would work out. But what about the y's? The y's are a little bit different. And so I have to do something slightly different. So essentially what I got to do is this idea is great. I got to go back and I got to upgrade the choice of the n's over here so that it works for not just for x, but also for y. Does anyone have an idea how we can do that? Yeah.
You could say like the maximum of fy of x, fy of x minus f of x, or fn of y minus f of y, and fn of x minus f of x has to be smaller than epsilon over 3.
Yes, this is exactly right. So actually, what I use here, look at, and this is the reason mathematics is written like this, where you always say what you're using, right? Like the thing that I got, I started with the pointwise limit of the fn's at the point x. But what it's pointing out is, like, I don't just need information at x, I need information at more than one point. And so I should not just start with the limit of the fn's at the point x, I should start out with the whole limit of the f's. So we're going to replace the conclusion, or the hypothesis over here. We're going to replace this with the limit as n goes to infinity of fn equals f in soup norm. And then we're, oh, we don't know that yet. We just know it's Cauchy. This is like what we want to get to. And then we want to replace this with this thing. We want to hold over all the maximum of x in AB. And then it'll hold, if it holds for the maximum, it'll hold for both x and y. So that's the idea. We're going to replace this with something that works for all the values, and we're going to get the conclusion we'll be working on all the values. Okay, so let me do a little like cut and paste here. We're going to put this line over here, and I'm going to cut this out. So obviously this will make your notes ugly, but I think is an instructive way to learn. Okay, so we're going to cut this out. I don't know how you want to write that. And we're going to replace that with this. And the thing that we're going to write, and the thing that we know is we know that Fn is Cauchy. So since Fn n equals 1 to infinity is Cauchy, so this is the replacement. Okay. Since Fn is Cauchy in AB in the soup norm, so L infinity of here, what this means is the maximum over all x in AB of Fn of x minus Fm of x is less than or equal to epsilon, and we can find at n, can find n so that for all nm greater than n, Fn minus Fm is less than epsilon. Okay, let me make sure this is exactly what they do in the textbook. Okay. Okay. And therefore, for all x in AB, Fn of x minus Fm of x is less than or equal to epsilon. So this is the key thing. When you go from max to pointwise, if it's true for the maximum, it's true for every single point. This is a key property of the max norm that we're using here. And now we're going to take this equation. This is saying for all n bigger than capital N, the absolute value of this thing is less than epsilon. And therefore, the limit as n goes to infinity is less than or equal to epsilon 2. So for all x in AB, I guess I could have made this even more clear, but let's make these less thans, and you're going to see that the less than becomes a less than or equal to. So if something is always less than epsilon for every single n value, then you can take the limit as n goes to infinity, and the limit could be less than or equal to epsilon. The limit could become equal to epsilon, but it's still less than or equal to epsilon. And this holds for all m greater than n. Okay, so for m beyond n, we take the limit as n goes to infinity. We can do that because it worked for all n beyond capital N. And so this thing is less than epsilon. But of course, the limit as n goes to infinity of this stuff, we can take the n inside. And this says the limit as n goes to infinity of Fn of x minus Fm of x is less than or equal to epsilon. And that is our function f. So for all x in AB, f of x minus Fm of x is less than or equal to epsilon. Okay. So we started with a less than epsilon. We ended up with a less than or equal to epsilon because we had to take the limit halfway, and the limit can achieve the thing, but that is good enough for what we want to do. And in this way, we have exactly what we want. We have the capital N, and there's an n for every m greater than capital N, f of x minus Fm of x is less than or equal to epsilon. And now it's working not just at the point x that was some fixed point, but it's working for every x. And now we can use it in the proof. So this replaces the choice of capital N from before. So this will be, we'll call this star. And then now if I go back up to the proof, maybe I'll leave it for a second if people are still copying down. But now when I go back up to the proof, remember the proof needed it at 2 different points, but it works for every single point, so it's all good. Okay. All right, let's go and recap over here. So this one is less than epsilon over 3. And then I could say these two are by star, and choice of n. And then the middle one is by dagger. Okay, and then I can give this equation dagger, by dagger, and choice of delta. Okay, so there we go. So by the continuity of capital N, we got the epsilon by 3 in the middle, and then by the approximation that was uniform for every single thing, it works at x and y. And so it's less than. Notice this one is, right, the middle one was less than or equal, but this one is a less than. So the whole thing is still a less than at the end, and that's equal to epsilon, and then we're happy. Okay, epsilon. Okay, and that's it. So that shows that f is continuous. Okay, let me zoom out a bit if people are still copying. Any questions or comments about that proof? Yeah.
I didn't get the last part of the
Yes, you want.
star or whatever.
Yeah. You just want to copy it down, you mean? Okay, yeah, fantastic. Okay. So that proves that the limiting function is continuous. By the way, this is closely related. There was a problem that I gave that said prove that the closure of continuous functions is still continuous functions. This is the same kind of argument you would use for that. There's one more thing we got to do, which is we got to prove. So this is claim. The limit as n goes to infinity of fn equals f in the L1 or L infinity norm. I keep saying L1. Okay. Okay. And the proof, I will say, I'm going to leave it as an exercise, but it is essentially the thing we did over here. So if you follow this argument and you copy it again, and you do it in the right way with the right thing that you're trying to prove, you will prove this by the same argument. So this little thing in the box was actually the proof that fn converges to f in the L infinity norm. Proof is going to be exercise, and this is a really good one for you to try and really work it out. Exercise, but see previous box because it has all the stuff you need to do. Okay. So altogether, this shows that if you have a Cauchy sequence of continuous functions, then you do the pointwise limit, and the pointwise limit exists. The pointwise limit, actually, because the original sequence was Cauchy, has to converge in L infinity, and the limit has to be continuous by doing this epsilon by 3 argument. Okay, and this shows that CAB is a complete space. Okay, questions or comments about that? Okay, in the last 10 minutes here, I want to talk about the thing that I left out last time, which are the LP spaces for L capital P. And let's talk about L1. So L1, say on 0, 1, is the set of functions. They're functions from 0, 1 to R. But the norm that we're using, the L1 norm, the F1, so if I take the norm L1, what I would like to integrate it from 0 to 1. And I would like to do the integral of the absolute value of f of x dx. Okay? So this is a new norm. You haven't seen this one yet. So far we've been doing the infinity norm. And this is a little bit like the norm in lowercase L1. In lowercase L1, you added them all up, and now you're integrating them. But here is the problem. Here is the big problem. L1 of 0, 1 is not complete with the Riemann integral. So if you want to try to do this integration, and your definition of the integral is the integral that you saw in first year calculus, and maybe again more rigorously in third year analysis, the Riemann integral, unfortunately it's not complete. In other words, you can have a sequence of functions that are Cauchy with this integral, and the limit is not is not there. And in fact, the limit is not even Riemann integrable. So we will see that the limit does not exist because, or let me say the limit is not in L1 because the limiting function is not Riemann integrable. So the space that I've avoided talking about until now is a bad space, sort of like doesn't do the things that you want. You cannot take limits in it. And when you watch the videos for this weekend, you will see that that means you cannot do infinite sums, and basically nothing will work. And sort of the blame is on Mr. Riemann. So the Riemann integral is not good enough. We need to upgrade our integral. We're going to upgrade to a better integral called the Lebesgue integral. And so the formula will be the same, just the interpretation of this integral symbol will be different. And with the Lebesgue integral, it will become workable. So it will be complete. We're actually going to have to do a little bit of, there's some small amount of shenanigans to do, even with the Lebesgue integral. But that is what we're going to do. So after you guys watch the videos for this weekend, we are more or less done with chapter 1. And then chapter 2 is all about constructing the Lebesgue integral and explaining what it is and why it works so that we can then work on the space L1 to get better things. And in fact, chapter 3 is all about the space L2, which is the same deal. So the L2 norm is this square norm that I teased in the first day of class. It's the integral of f of x squared dx. And it's the same problem as L1. So when we solve this problem for L1 by upgrading the Riemann integral to the Lebesgue integral, then we will be ready to talk about L2 functions and prove our Fourier series thing. Okay. The midterm is essentially on all the stuff from chapter 1. I will post everything that is covered. So you have to watch the videos for this weekend, do the problems on Tuesday, and then Thursday will be like a review or something, or like maybe I missed something and I'll check that out. Okay, any questions or comments before we break? Yeah.
Are you going to post this?
I have, yeah, so I record the lectures, or at least I try to. Sometimes they don't work, and I can also post the PDF of the notes if you guys want. Yeah. Okay. Okay, great. So we'll see everybody on Tuesday. Make sure you watch the videos and come prepared for the quiz and problems on Tuesday.